Hey everyone, welcome back. So we are looking to finish this up and trying to figure out how soap works on a virus. We looked at soap, the structure of soap, and the structure we looked at oil and water and polar and non-polar things. And now we're going to start looking at how soap interacts with a virus. So this is a model that was developed. It's a model that has been used in several publications, but this is from the New York Times, and this is a picture of what a virus, a spike virus, might kind of look like, similar to what COVID is. And so I want you to take a look at it. In the picture, you'll see that there is a layer right here, which is a lipid, and lipids are usually non-polar. And so I want you to use your knowledge about non-polar things. What do we know about non-polar things, and how the soap molecule might interact? So think about how things interact with each other, polar and non-polar. This next slide is going to look at a simplified version of a soap molecule. So how does this compare to this? We're going to write about that. What do you see going on here with those two pictures? And why might I use this as part of the model? And then we're going to take a look at what happens when soap starts to attack a virus. So in this picture, you're going to just write about what you see happening here, and pay particular attention to the interactions. So this is going to be your chance to really use your knowledge of how models are set up, interpreting what a model is showing. What do I notice about how these are organized? Are they, what arrangement are they in? What's going on with this? Remember, this is a non-polar layer. So what's going on with these soap molecules to attack this non-polar layer of the virus? And then here, what's going on when I have this spike protein in the middle here? Some spike protein, some lipid. Why are all these soap molecules facing this direction? Okay, so that's the next thing. And then finally, when you have the soap particle, when you have the soap particles surrounding these parts of the virus, well, when I wash my hands, so washing your hands, you use soap and then you use water at the end, and this water is going to wash this away. So what role does the water play now? Remember, water is a polar molecule, so that means it's got charges there, plus and minus charges. What role does the water have, and why is it important that all these soap particles are facing this outward direction? They're kind of grabbing onto this thing, so why is it important that they hold on that way? Okay, and then finally, going back to the original question, well, we have soap and sanitizer. So sanitizer is this particle right here, and this is soap. You can see that lots of C's and H's. Sanitizer, only two of them. So if I was to draw a model of the sanitizer particle, how would that look compared to this soap particle? What would be similar? What would be different? And then, why do you think sanitizer does not work as well on the virus as soap would? Okay, so those are some questions that you're going to be answering today. And then I want to tie it back to the last unit. So if you remember in our last unit, let me move this out of the way a little bit. Our last unit, we had, we were looking at bonds. And so I want to be thinking about now, what are some differences between attractions and bonds. So if I have water, this is a water molecule right here, and water has charges. So charges here, charge here, and we can see that between, this is a water molecule here, this is another water molecule. So between individual water molecules, there's this dashed line. And this dashed line we're going to call an attraction. Okay? But within the molecules is water. This is a bond. So this bond holds water together. If I don't have a bond there, it's no longer water. It is something different. And so attractions are between the larger clumps of molecules. A bond is within the molecule. Okay, so here is what we're talking about with attractions versus bonds. This is kind of a really difficult concept to get, but in the last simulation we had, when you have the dashed line, so this is an attraction, okay? If I have molecules right here, those are attractions, and when I start moving things close together, these charges, these plus and minus charges, they start pulling together. So this is kind of like a water molecule right here. Water molecules have plus and minus sides to them, and they start getting these it's like two magnets, and you put them together, and you can feel them pulling together. Okay, when I pull them apart, it now has less attractions. What we're doing now is we're starting to compare what is the difference between an attraction and a bond. So if I have, this is a water molecule, I can pull it apart, and now I've broken the attraction, but the bond, this thing right here, this is a bond. This is a bond. This is a bond. So those are bonds. They stay together, and that's a different thing. That's what happens when I have electrons that are being shared. So if you remember for the break, we had this simulation. This showed two atoms. So we have this atom here, this atom here. Remember, an atom has a nucleus, which is positive charge, and we have electrons on the outside, which are negative charge. And so remember, positive and negatives attract each other, and as I push them closer together, so I'm going to move these a little closer together, they start attracting. So we have positives, the positive nucleus starts attracting the negative electrons, and vice versa. These negative electrons start attracting the positive nucleus. So they start shifting. And as they move closer and closer together, now they start overlapping. So these attractive forces are being pulled together, and the potential energy, it starts to go down. It becomes good to have attractive forces because we don't want things far apart. But then if I push them too close together, they start repelling. So remember, negatives repel, positives repel, and now we have repulsive forces. So there's this perfect point. If I push them together, attract, 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 a little bit of repulsive force right here, and then we have this balanced state. And when they are balanced, when I have this nucleus and this nucleus perfectly balanced, it's very similar to when I have this simulation here. If I reset this, this simulation where I have the atoms, this is like the bond that you see there with the two nuclei. I have this bond right here. That, in essence, is this thing right here. Okay? So a bond is the balance point at which two nuclei have come together, and the electrons and the attractive and repulsive forces have balanced out each other. And we're going to look and see how can I tell what the difference between an attraction and a bond is.